Iterative improvement. The iterative improvement process involves the development of imperfect initial version up until basic operation. The first version serves as an initial beginning point that functions as a preliminary test. The first version becomes the starting point to identify which single element requires improvement for slight enhancement. To make that small adjustment, to carry out this procedure multiple times where you examine new version and select additional minor improvements before implementing such changes. Keep following this method repeatedly by analyzing the condition first and then selecting a minor enhancement before making that adjustment. The iterative process advances your creation gradually because it allows clear to superior result and enhance final output. The process stops only when your results meet your satisfaction criteria or small improvements possibilities become too elusive to identify. The method works by improving through multiple steps instead of attempting a final perfect outcome in a single action. Real-life example or problem. The problem of assigning 4 available final year projects that students Ali, Ben, Chloe, and Dana requires a single paragraph explanation. A critical responsibility exists for us to distribute students through open final year project position. 4 students, namely Ali, Ben, Chloe, and Dana, require assignments of separate subjects separated into artificial intelligence or AI, robotic and web development or web dev, data science group. Each student's assignment depends on their areas of interest as well as qualification because Ali aims for AI and robotics development prefers robotics in combination with field dev, web dev, and Chloe selects web dev paired with data science and Dana only wants to work with AI projects. Students and projects create a bipartite graph matching pattern through which edges link students to projects matching their interests. The goal is to find the maximum number of student project assignments where each member of the project obtains only one assignment to their preferred project.
The student project assignment process improves through iterative refinement, aiming to maximize the number of successful matches or the matching size. Initially, 3 students are matched: Ali in AI, Ben in robotics, Chloe in web development. This leaves Dana unassigned, since AI is one of Dana's interests but already taken by Ali. The algorithm searches for an augmenting path, a sequence of swatch that can lead to a better overall assignment. So here's the path found. Dana wants AI. Ali switches to robotics. Ben switches to web development. Chloe switches to data science, which is unassigned. So by flipping these assignments, we get Dana in AI, Ali in robotics, Ben in web development, and Chloe in data science. Now, all 4 students have a project they like. No one is left unassigned, and no further improvements are possible. The algorithm ends with a maximum matching of 4.
So let's now go to the bipartite matching using iterative improvement augmenting paths approach. So we have this called the student preference as adjacent series, the bipartite graph. So we have the graph. The Ali is interested in AI and robotics, and Ben is interested in robotics and web dev, and Chloe is interested in web dev and data science, and Dana is interested only in AI. So we're now going to dictionary to store which project is assigned to which student. So we define this: a match result is equals to null, or the key project is the value of student assigned to it. So in recursive function, to find if the student can be assigned a project, we define the can assign student and the visited. So iterate through each project. The student is interested in. For project, we're going to the for loop now. For project in graph, a student it will check if the project has not been visited in this path. If the project not in the visited will add the project. It will mark the project as visited, and it will go to other if statement that the if it will check if the project is unassigned for or can be reassigned. So if the project not in match result or can assign the match result of the project will visited. So it will return true if the assignment successful, and return false if the project if no project could be assigned to the student. So we'll go to the main function of the def. We define the max matching. So we try to find the an assignment for each student. So for student in graph, visited is equals to set. It will keep the track of visited project on this iteration, and can assign the student or the visited, and it will attempt to assign a project to the student. So the max matching, it will run as a matching algorithm. So it will display the result. It will print the final student project assignment maximum matching if we display the result, and for each statement um, for project is equals to student in match result, that items it will print the f student is minus equals to the project. So we see in the output, or we see the final student project assignment, the maximum matching is Dana has AI, and Ali has a robotics, and Ben is in a web dev, and Chloe is in a data science. So that's the output of the final student project of our code.
As for our results, our method worked very well and clearly showed that iterative improvement is a great way to solve the maximum matching problem in bipartite graphs. At first, we had a matching where only 3 out of 4 students got a project they liked. One student was left without a match, so the result wasn't the best it could be. To fix this, we used iterative improvement. This means we looked for a better way to match students and projects by finding something called an argument path. When we found this path, we flipped the matches along it, which gave us a new and better arrangement. In the end, all 4 students got a project they liked and no projects were left out or used more than once. This final result is the best possible one. It matched each student to a different project with no repeats or empty spots. It used all available projects in the smartest way and made sure everyone was happy with their match. This shows that iterative improvement really does work well for this kind of problem. It's not only a good method, it's one of the best. It helps us find better answers step by step without having to try even a single option like in brute force methods, which can take a long time. This way of solving problems is also useful in real life. It can help match students to school projects, people to jobs, or workers to schedules, whenever we need to make the best matches between two groups. Iterative improvement is a smart and simple method that gets the job done well.